When we hear the word isolated, we usually think about something familiar. A lonely house far from a city, a village deep in the mountains, a person living without neighbors. On Earth, isolation feels large because our world is small. A few kilometers can separate people. A few hours of travel can feel like a great distance. But in space, the meaning of isolation changes completely. Isolation in space is not about being far by human standards. It is about being far on a scale so large that the human mind struggles to imagine it. To understand what an isolated galaxy really is, we first need to understand distance in the universe. On Earth, we measure distance in meters, kilometers, or miles. Even when we talk about space nearby, we use distances like the distance to the moon or the distance to the sun. These numbers already feel huge. The moon is about 384,000 kilometers away. Light takes just over 1 second to reach it. The sun is about 150 million kilometers away, and light takes about 8 minutes to travel that distance. But galaxies exist far beyond these scales. Galaxies are so far apart that scientists measure distance in light years. 1 light year is the distance light travels in 1 year. Light moves incredibly fast, about 300,000 kilometers per second. Even at that speed, it takes 1 full year to travel 1 light year. This already tells us something important. Space is enormous. Our home galaxy, the Milky Way, is about 100,000 light years wide. That means light needs 100,000 years just to cross it from one side to the other. And yet, the Milky Way is not alone. It has neighbors, many neighbors. The closest large galaxy to us, Andromeda, is about 2.5 million light years away. This distance sounds unbelievable, but in cosmic terms it is considered close. The Milky Way and Andromeda are part of a small family called the Local Group. This group contains dozens of galaxies, all bound together by gravity. They are neighbors in the universe. This brings us to an important idea. Galaxies usually live in cosmic neighborhoods. Just like cities on Earth form countries, and countries form continents, galaxies form groups, clusters, and superclusters. Gravity pulls them together over billions of years. Where matter is slightly denser, galaxies form closer together. Over time, these regions grow crowded. Most galaxies you see in telescope images are not alone. They are surrounded by other galaxies. Some are so close that they are actively interacting. Their gravity stretches one another, pulls stars away, and sometimes causes dramatic collisions. These interactions shape how galaxies look and behave. Because of this, true isolation is rare. An isolated galaxy is not just one that is a little far from others. It is a galaxy that exists without close neighbors for millions or even tens of millions of light years. It has not interacted with another galaxy for a very long time, sometimes since the early universe. It has lived its life quietly, without major disturbances. To understand how extreme this is, imagine Earth again. Imagine the nearest city to you was not a few kilometers away, not even thousands of kilometers away, but millions of kilometers away. Imagine that even if you traveled at the fastest speed possible, it would take years just to reach the closest neighbor. That is what isolation means in space, and it goes even further. In some cases, isolated galaxies live inside vast regions called cosmic voids. These voids are enormous areas of space where very few galaxies exist. They can be hundreds of millions of light years across. Inside them, galaxies are sparse, faint, and widely separated. These are the emptiest places in the universe. So why does the universe have neighborhoods at all? The answer goes back to the beginning. After the Big Bang, matter was not spread evenly. Tiny differences in density existed. Some regions had slightly more matter than others. Over time, gravity pulled matter toward these denser regions. Gas collected, stars formed, galaxies grew. Where matter was dense, galaxies formed close together. Where matter was thin, very little formed. This process created a universe with structure. Not random chaos, but a giant web. Scientists call it the cosmic web. Galaxies line up along filaments like glowing threads, while enormous voids stretch between them. Most galaxies live along these filaments. They are part of the cosmic traffic. They feel the pull of many neighbors. They grow by stealing gas, merging with others, and constantly changing. But some galaxies formed far from these busy regions. They were born in quiet places, places where gravity was weaker, places where there was less matter to pull them toward crowds. Over billions of years, they stayed there, alone. This is why isolation in the universe is not just about distance, it is about history. An isolated galaxy is isolated because it missed out on interactions. It was never pulled into a group. It never collided with a neighbor. It never experienced the chaos that shapes most galaxies. Its life story is slow, calm, and quiet. This also explains why isolation is rare. Gravity loves to gather things together. Over time, it reduces loneliness. It pulls matter into clumps. It creates families of galaxies. For a galaxy to remain isolated for billions of years, it must be in a very special place, with very specific conditions. That makes isolated galaxies incredibly valuable to scientists. They act like control experiments. When you want to understand how something evolves, it helps to study it without outside influence. Isolated galaxies show us what happens when a galaxy grows without interference. No mergers, no close encounters, no dramatic events. By comparing isolated galaxies with crowded ones, astronomers can see how environment shapes everything. Shape, size, star formation, brightness, and even lifespan. So when we say a galaxy is isolated, we are not just saying it is lonely. We are saying it lives in a different kind of universe. A universe where distances are vast beyond imagination, where time moves slowly, where change happens quietly, where gravity whispers instead of shouting. To truly understand what makes an isolated galaxy special, we first need to look at how galaxies normally live. In most parts of the universe, galaxies are not alone. They are social objects, shaped by gravity and surrounded by neighbors. Just like people tend to gather in cities, galaxies tend to gather in groups and clusters. Living together is the natural state of the universe. When astronomers map the universe on large scales, they do not see galaxies scattered randomly. Instead, they see patterns. Long chains of galaxies stretch across space, connecting dense regions like glowing highways. These chains meet at massive intersections filled with hundreds or even thousands of galaxies. Between them are vast empty regions called voids. This structure is known as the cosmic web, and it defines how galaxies live and move. At the smallest level of this structure are galaxy groups. A galaxy group is a small family of galaxies held together by gravity. These groups usually contain a few large galaxies and many smaller ones. They are relatively calm environments compared to massive clusters, but interactions still happen often. Galaxies in groups pass close to one another, exchange gas and slowly change over time. Our home, the Milky Way, lives in such a group. The Milky Way is part of the Local Group, a collection of more than 50 galaxies spread across a region about 10 million light-years wide. The two largest members are the Milky Way and the Andromeda Galaxy. Around them orbit dozens of smaller galaxies called dwarf galaxies. Some are so faint that they were only discovered recently with powerful telescopes. In cosmic terms, the Milky Way is not isolated at all. It has neighbors in every direction. Gravity binds this group together, and the galaxies inside it are constantly interacting, even if those interactions happen slowly. For example, the Milky Way is pulling in smaller dwarf galaxies right now. Streams of stars around our galaxy are evidence of past mergers, where smaller galaxies were torn apart and absorbed. This brings us to one of the most important ideas in astronomy. Gravity is a social force. Gravity does not push things apart, it pulls them together. Any object with mass feels gravity, and galaxies have enormous mass. Not only do they contain billions or trillions of stars, but they also sit inside massive halos of dark matter. These halos extend far beyond the visible edges of galaxies, increasing their gravitational reach. Because of this, galaxies influence each other, even when they are far apart. Over millions or billions of years, gravity slowly pulls galaxies closer together. Paths curve, speeds change. Eventually, close encounters happen. This is why galaxies usually interact. In a crowded region of space, a galaxy is never truly alone. Even if it is not colliding with another galaxy at this moment, it is feeling the combined gravitational pull of many neighbors. This affects how it moves, how it spins, and how it evolves. As galaxies drift through groups and clusters, they experience gravitational encounters. These encounters do not always result in collisions, but they can still have powerful effects. A close pass can stretch a galaxy, pulling long streams of stars out into space. Gas can be stripped away or compressed, triggering bursts of new star formation. Over time, repeated encounters slowly reshape galaxies. In larger environments, such as galaxy clusters, these effects become even stronger. Galaxy clusters are the largest gravitationally bound structures in the universe. They can contain hundreds or even thousands of galaxies packed into a region only a few million light-years across. In these dense environments, galaxies move at very high speeds, often thousands of kilometers per second. Inside clusters, interactions are frequent and intense. Galaxies rush past one another, feeling strong gravitational forces. Hot gas fills the space between galaxies, and as galaxies move through this gas, it can strip away their own gas like wind stripping leaves from a tree. This process can shut down star formation, turning once bright blue galaxies into quiet red ones. Clusters are chaotic places. Galaxies there rarely live calm lives. One of the most dramatic outcomes of living together is galaxy collisions and mergers. When two galaxies collide, it does not look like a crash in the everyday sense. Stars are so far apart that they almost never hit each other directly. Instead, gravity does the damage. The shapes of the galaxies distort. Long tails of stars stretch out into space. Gas clouds collide and compress, triggering massive bursts of star formation. Over time, the two galaxies can merge into one larger galaxy. This process has shaped the universe since its earliest days. Many of the large galaxies we see today were built through multiple mergers. Each merger leaves behind clues in the structure of the galaxy, in the motions of its stars, and in the distribution of its gas. Our own Milky Way is a product of this shared evolution. Astronomers know that the Milky Way has merged with many smaller galaxies in the past. It is doing so even now. In the distant future, it will merge with Andromeda, forming a single giant galaxy. This is not an unusual event. It is a normal part of how galaxies live and grow. Shared evolution means that galaxies influence each other's futures. When galaxies interact, they change one another. A galaxy that might have formed stars slowly on its own can suddenly experience a burst of activity after a close encounter. Another galaxy might lose its gas and become quiet forever. Shapes change from graceful spirals to smooth, rounded forms. Colors shift from blue to red. Environment matters. Where a galaxy lives determines much of what it becomes. A galaxy in a dense cluster will evolve very differently from a galaxy in a quiet group, and both will be very different from a galaxy living in isolation. This is why isolation stands out so strongly. When we look at most galaxies, we see signs of interaction. Bent arms, distorted shapes, streams of stars, evidence of past mergers. These features tell a story of a crowded universe where gravity constantly pulls galaxies together. Isolated galaxies lack many of these signs. They are not stretched by close neighbors. They are not shaken by frequent encounters. Their evolution is slow and steady. To truly appreciate how unusual this is, we must remember that the universe naturally pushes galaxies toward togetherness. Gravity does not favor loneliness, so when we find a galaxy that has lived alone for billions of years, we are not just finding something distant, we are finding something rare, something that escaped the normal rules of cosmic society. When we imagine the universe, we often picture it filled with galaxies everywhere. Bright spirals, glowing clouds of stars, clusters packed tightly together. Telescope images reinforce this idea. They show crowded regions where galaxies seem to touch and overlap, filling space with light. But this picture is incomplete. Between these bright regions lies something just as important and far more mysterious: vast emptiness. These enormous empty regions are called cosmic voids, and they are some of the largest structures in the universe. They are not small gaps, they are not empty corners. They are huge regions of space where almost nothing exists. To understand cosmic voids, imagine the universe as a giant three-dimensional web. Galaxies are not spread evenly. Instead, they trace out long filaments and sheets, like threads of light stretching across darkness. Where these filaments intersect, galaxy clusters form. Where they do not, vast empty bubbles appear. These bubbles are cosmic voids. A cosmic void is a region of space with very few galaxies. Compared to crowded galaxy clusters, voids can seem almost completely empty. In some voids, there may be only a handful of small faint galaxies scattered across enormous distances. In others, there may be none at all. But voids are not small. Some cosmic voids are tens of millions of light years across. Others stretch for hundreds of millions of light years. To put that into perspective, the Milky Way galaxy is about 100,000 light years wide. A single large void could fit thousands of Milky Way galaxies side by side and still have room left over. When astronomers map the universe on the largest scales, they find that voids take up most of the volume of space. Even though galaxies contain most of the visible matter, most of the universe by volume is empty. The universe is more void than substance, so why do these voids exist? The answer goes back to the very beginning of time. Shortly after the Big Bang, the universe was hot, dense and filled, almost uniformly with matter and energy. But it was not perfectly smooth. Tiny differences existed in density. Some regions had slightly more matter, others had slightly less. These differences were incredibly small, but gravity amplified them over billions of years. Where matter was slightly denser, gravity pulled more matter in. These regions grew into filaments, groups, and clusters of galaxies. Where matter was slightly less dense, gravity pulled matter away toward the denser regions. Over time, these underdense regions became emptier and emptier. This process created cosmic voids. In simple terms, voids are places where matter was never abundant to begin with. As gravity pulled matter toward denser regions, voids lost even more material. They became the quiet spaces left behind as the universe organized itself. Cosmic voids are not static. They evolve. As the universe expands, voids grow larger. Matter continues to flow outward from them, toward filaments and clusters. In this way, voids slowly expand like bubbles in rising bread dough. Over billions of years, they become emptier and larger, while galaxies become more concentrated along their edges. This expansion plays an important role in shaping the universe we see today. Now, an important question arises: are cosmic voids completely empty? The answer is no, but they come close. Voids still contain dark matter, gas and radiation. They are not true nothingness. However, the density of matter inside voids is extremely low compared to the rest of the universe. Galaxies inside voids are rare, widely spaced, and often small. The galaxies that do exist inside voids are usually very different from those in crowded regions. Void galaxies tend to be faint, small, and isolated. They often have simple shapes and show fewer signs of interaction. Many are dwarf galaxies with weak gravity, unable to attract neighbours or grow quickly. Some are gas-rich but form stars slowly. Others barely form stars at all. Life inside a void is quiet. There are no frequent encounters, no close passes, no violent mergers. A galaxy inside a void can go billions of years without ever coming near another galaxy. In some cases, the nearest neighbour may be tens of millions of light years away. This makes voids the perfect home for isolated galaxies. Isolation requires distance, and voids provide distance on the largest scale possible. If a galaxy forms near a filament or cluster, gravity will eventually pull it inward. Over time, it will become part of a group or cluster, but a galaxy that forms deep inside a void experiences a very different fate. The gravitational pull from outside is weak. There are no nearby massive galaxies to draw it in. It remains where it formed, drifting slowly through empty space. This is why the most isolated galaxies are often found inside or near the centers of cosmic voids. These galaxies are not just far from others, they are surrounded by emptiness in every direction. Studying voids helps astronomers answer some of the biggest questions in cosmology. Voids act as natural laboratories. Because they contain so little matter, they allow scientists to study the universe under simpler conditions. The effects of gravity, dark matter, and cosmic expansion are easier to isolate. There is less interference from complex interactions. For example, voids help scientists test models of dark energy, the mysterious force causing the universe's expansion to accelerate. Because voids expand differently than dense regions, their size and shape provide clues about how dark energy behaves. Voids also help scientists understand galaxy formation. By comparing galaxies inside voids with those in clusters, astronomers can see how environment shapes evolution. A galaxy in a cluster may stop forming stars early due to gas stripping and interactions. A galaxy in a void may continue forming stars slowly for billions of years. These differences reveal how much environment matters. Another fascinating aspect of voids is their silence. In crowded regions, galaxies are constantly exchanging material. Gas is stripped, heated, and shocked. Radiation is intense. In voids, these effects are minimal. The radiation environment is calmer. Gas clouds can remain undisturbed for long periods. This makes void galaxies some of the most pristine objects in the universe. They are not perfect time capsules, but they come close. Because void galaxies experience fewer interactions, they preserve information about early galaxy formation. Their structure, chemistry, and star populations can reflect conditions that existed billions of years ago. This is one reason astronomers search so carefully for isolated galaxies in voids. But finding them is not easy. Void galaxies are faint and distant. They emit less light. They are spread across enormous regions of space. Detecting them requires deep surveys and sensitive instruments. Even today, many void galaxies remain undiscovered, hiding in the darkness between brighter regions. As technology improves, astronomers are finding more of them. Each new discovery helps refine our understanding of how the universe evolved. Cosmic voids may seem empty, but they are full of meaning. They show us how the universe organizes itself. They reveal the balance between gravity and expansion. They provide homes for the loneliest galaxies ever formed. And perhaps most importantly, they remind us of scale. The universe is not just filled with objects. It is shaped by absence, by the spaces between things, by regions where almost nothing happens for billions of years. In these silent regions, isolated galaxies drift slowly, unchanged, untouched, carrying stories from a quieter universe. When we look at an isolated galaxy drifting quietly through space, it is tempting to think that it chose this lonely path. But galaxies do not choose. They follow gravity, chance, and the conditions set at the very beginning of the universe. Isolation is not a decision. It is the result of a long chain of events that began billions of years ago. To understand why some galaxies end up alone, we must travel back to the early universe, just after everything began. In the earliest moments after the Big Bang, the universe was hot, dense, and filled with energy. Matter existed mostly as simple particles spread almost evenly through space. Almost evenly, but not perfectly. Tiny differences existed. Some regions had a little more matter, others had a little less. These differences were incredibly small, far smaller than anything we could notice today. But gravity noticed them. Gravity always pulls matter toward matter. Over time, regions with slightly more matter began to attract more material. Gas flowed in, dark matter gathered. These regions grew denser and denser. Eventually, they became the birthplaces of stars and galaxies. Meanwhile, regions with slightly less matter lost material. Gravity pulled matter away from them toward the denser regions. This simple process set the stage for everything that followed. Some parts of the universe were destined to become crowded. Others were destined to become quiet. Galaxies that formed in dense regions were surrounded by other forming galaxies. Their paths crossed early. They interacted, merged, and grew together. Galaxies that formed in low-density regions experienced a very different fate. They had fewer neighbors, less nearby matter, weaker gravitational pulls from outside. These early conditions mattered more than anything else. A galaxy's environment at birth strongly influences its entire life. If a galaxy forms near a filament of the cosmic web, it will likely be drawn into a group or cluster over time. Gravity will guide it toward other galaxies. Encounters will happen. Growth will be fast and dramatic. But if a galaxy forms in a region where matter is sparse, it may never experience these interactions. This is where isolation begins. One key reason galaxies end up alone is missed interactions. In crowded regions, galaxies pass close to one another frequently. Even a distant pass can alter a galaxy's path. Gravity bends trajectories. A near miss can pull a galaxy into a group. Over billions of years, small changes add up, but in empty regions, close passes are rare or non-existent. A galaxy may simply never come close enough to another to feel a strong gravitational tug. It drifts along its original path, largely unchanged. Imagine two boats on a calm ocean. If the ocean is crowded with currents and waves, the boats will eventually move toward each other or be pushed together. But if the ocean is almost perfectly still and the boats start far apart, they may never meet at all. They will drift quietly, separated forever. That is what happens to galaxies in empty regions of space. Missing interactions also means missing opportunities to grow. Galaxies grow in two main ways. They form stars from their own gas, and they gain mass by merging with other galaxies. In crowded environments, mergers are common. Large galaxies grow quickly by absorbing smaller ones. Their structure becomes complex. Their star populations become diverse. Isolated galaxies miss out on this process. Without mergers, their growth is slow. They rely mostly on the gas they were born with. Star formation happens steadily, but not explosively. Over time, gas may slowly be used up, and star formation may fade. This leads to quiet lives. Isolated galaxies tend to be calmer. They show fewer signs of disturbance. Their shapes are often simple and symmetrical. Their stars move in orderly patterns. There are fewer violent events to disrupt them. This does not mean isolated galaxies are inactive. They still form stars. They still evolve, but they do so at a slower pace, guided by internal processes rather than external forces. Another major reason galaxies end up alone is the way gravity pulls matter elsewhere. Gravity does not act evenly across the universe. Dense regions exert strong gravitational pulls. Over billions of years, matter flows toward these regions. Gas, dark matter, and even entire galaxies slowly migrate inward. This leaves some areas depleted. If a galaxy forms in a region where gravity from outside pulls material away more strongly than it pulls inward, the galaxy may be left behind. Surrounding matter drains toward filaments and clusters. The galaxy remains in an increasingly empty region. As time passes, this emptiness grows. The universe is expanding, and this expansion stretches space itself. As space stretches, distances between galaxies increase. In dense regions, gravity can overcome this expansion and keep galaxies together. In low-density regions, gravity is too weak. Expansion wins. This means that galaxies in voids become more isolated over time, not less. Even if a galaxy had distant neighbors billions of years ago, cosmic expansion may have carried them farther and farther apart. Eventually, the distances become so large that interactions are effectively impossible. In this way, isolation increases with age. Another important factor is dark matter. Galaxies are surrounded by halos of dark matter that extend far beyond their visible edges. These halos help pull galaxies together. In dense regions, dark matter halos overlap and interact strongly, guiding galaxies into groups and clusters. In voids, dark matter is sparse. Halos are smaller and more isolated. Without strong dark matter connections, galaxies lack the gravitational bridges that lead to interactions. This further locks them into solitude. All of these factors point to one conclusion. Isolation is an accident of cosmic history. It is not something that happens suddenly. It is not caused by a single event. It is the result of where a galaxy was born, how much matter surrounded it, and how gravity shaped its path over billions of years. Some galaxies were simply unlucky or lucky, depending on how you see it. They were born in quiet places. They missed encounters that could have changed their fate. They drifted through expanding space while matter flowed away from them. Over time, they became some of the loneliest objects in the universe. Yet this loneliness gives them special value. Because they have lived quiet lives, isolated galaxies preserve information that crowded galaxies lose. Their stars are not mixed and reshuffled by mergers. Their gas is not stripped away by close encounters. Their structure reflects internal evolution rather than external chaos. They are shaped more by time than by violence. In a universe where most growth comes from interaction and collision, isolated galaxies show us another path. A path of patience, of slow change, of subtle evolution. They remind us that the universe does not evolve in one single way. There are many paths written into cosmic history, determined by tiny differences at the very beginning of time. Among all the lonely galaxies scattered across the universe, there is one that stands out as an extreme case. A galaxy so isolated that it seems almost forgotten by the rest of the cosmos. No close neighbors, no nearby companions, no signs of interaction for most of its life. When astronomers discovered it, they were stunned. This galaxy challenged many assumptions about how galaxies form and survive. This galaxy is known as KKR 25. It is not famous for its beauty. It is not large or bright. In fact, it is quite the opposite. KKR 25 is a small, faint dwarf galaxy, and yet it has become one of the most important objects in the study of cosmic isolation. To understand why KKR 25 shocked astronomers, we must first understand where it lives. KKR 25 is located in a region of space known as the local void. This void is a vast, underdense area near our own cosmic neighborhood. While the Milky Way and Andromeda sit in a relatively busy region, the local void lies nearby as a massive zone of emptiness where very few galaxies exist. KKR 25 sits deep inside this void. It is located roughly 6 to 7 million light-years away from the Milky Way, which might not sound extremely far by cosmic standards. But distance alone does not define isolation. What matters more is how far it is from other galaxies, and this is where KKR 25 becomes extraordinary. The nearest significant galaxy to KKR 25 is millions of light-years away. There are no nearby companions, no small satellite galaxies, no signs of a group or cluster. For a dwarf galaxy, this is almost unheard of. Most dwarf galaxies live near larger galaxies. They orbit giants like the Milky Way or Andromeda. Over time, they are pulled in, stretched, and sometimes destroyed. Many dwarf galaxies we know are survivors of these violent environments. KKR 25 is different. It lives completely alone. This level of isolation makes it one of the most isolated galaxies ever discovered. It has likely spent most of its existence without interacting with another galaxy in any meaningful way. Now comes the next question. How did scientists even find such a faint, lonely object? Discovering isolated galaxies like KKR 25 is extremely difficult. These galaxies are dim, small, and spread across enormous distances. They do not announce themselves with bright light or dramatic shapes. They hide in darkness. KKR 25 was discovered through careful sky surveys that looked for faint objects moving differently from nearby stars. Astronomers use sensitive telescopes to detect its light and analyze how it moved through space. By measuring its distance and velocity, they confirmed that it was not a satellite of any nearby galaxy. This was a crucial step. At first, scientists wondered if KKR 25 might simply appear isolated from our point of view, but actually be connected to a larger system. But detailed observations showed that it truly was alone. Its motion did not match that of nearby galaxy groups. It was not falling toward any massive neighbor. It was drifting quietly in the void. Once astronomers realized how isolated KKR 25 was, the questions multiplied. According to many theories, dwarf galaxies like KKR 25 should not survive alone for long periods. Without interactions, they were expected to retain gas and continue forming stars slowly. Or, if they lost their gas early, they should show signs of environmental effects. But KKR 25 did not behave as expected. KKR 25 is classified as a dwarf spheroidal galaxy. These galaxies usually lack gas and show little to no ongoing star formation. They are often found near massive galaxies where gravitational forces strip away their gas and shut down star formation. Finding a dwarf spheroidal galaxy in complete isolation was shocking. There was no nearby massive galaxy to strip KKR 25 of its gas. No cluster environment to shut down its star formation. And yet, KKR 25 appeared quiet and inactive, with an old population of stars and very little gas. This raised a profound question. How did KKR 25 lose its gas? This discovery challenged the idea that environment alone determines a galaxy's fate. If KKR 25 could become a quiet, gas-poor galaxy without external influence, then internal processes must play a bigger role than previously thought. Perhaps early star formation used up its gas. Perhaps stellar winds and explosions pushed gas out of the shallow gravitational well of the galaxy. Perhaps the early universe itself was harsh enough to remove gas from small galaxies, even in isolation. KKR 25 became evidence that isolation does not always mean simplicity. Another reason KKR 25 shocked astronomers was its age. The stars inside KKR 25 are mostly very old. This suggests that it formed stars early in the universe's history and then slowed down dramatically. It has lived quietly for billions of years, evolving internally rather than through interaction. In crowded environments, such a long, undisturbed history would be nearly impossible. KKR 25 is like a fossil. It preserves information about how small galaxies formed in the early universe, before interactions became common. It allows scientists to study galaxy evolution in a nearly pure form, free from the complications of mergers and tidal forces. This makes KKR 25 incredibly valuable. It is not impressive because it is large or bright. It is impressive because it exists at all. For decades, astronomers believed that dwarf spheroidal galaxies required external forces to become what they are. KKR 25 showed that isolation alone does not guarantee an active, star-forming galaxy. Nature is more complex. KKR 25 also changed how scientists think about void galaxies. Before its discovery, many believed that galaxies in voids would mostly be gas-rich and actively forming stars. KKR 25 proved that even in the quietest environments, galaxies can follow unexpected evolutionary paths. It suggested that some galaxies are shaped more by their internal history than by their surroundings. In many ways, KKR 25 represents the extreme edge of galaxy evolution. It formed early, it missed interactions, it lost its gas, it aged quietly, and it did all of this alone. When astronomers find galaxies like KKR 25, they are reminded that the universe does not always follow simple rules. Patterns exist, but exceptions matter. Those exceptions reveal deeper truths. KKR 25 is not just the most isolated galaxy ever found. It is a reminder that cosmic loneliness can produce surprising outcomes. As telescopes become more powerful and surveys become deeper, astronomers expect to find more galaxies like KKR 25 hidden in voids, drifting silently through space. Each one will help refine our understanding of how galaxies form, evolve, and survive. When people imagine galaxies, they usually picture grand spirals with sweeping arms, or massive glowing ellipses packed with stars. These are the galaxies that dominate astronomy images and documentaries. But these giants are only part of the story. In fact, they are the minority. Most galaxies in the universe are much smaller, quieter, and harder to see. These are called dwarf galaxies, and they are the true building blocks of the cosmos. To understand isolated galaxies, we must understand dwarf galaxies first. Many of the most isolated galaxies ever found belong to this small and humble category. A dwarf galaxy is exactly what the name suggests. It is a galaxy with far fewer stars than giants like the Milky Way. While the Milky Way contains hundreds of billions of stars, a dwarf galaxy may contain only a few million, or even just a few 100,000. Some are so faint that they barely glow against the darkness of space. Dwarf galaxies come in many forms. Some are small spirals, some are irregular, with no clear shape. Others are smooth and rounded, known as dwarf spheroidal galaxies. Despite their differences, they all share one thing in common. They are small, fragile, and strongly influenced by their surroundings. This is why many dwarf galaxies are found orbiting larger ones. In crowded regions of the universe, dwarf galaxies rarely live independent lives. Their weak gravity makes them easy targets for larger neighbors. As they drift close to massive galaxies, they feel strong gravitational forces. Gas is stripped away, stars are pulled out. Over time, many dwarfs are torn apart completely and absorbed. This process has happened countless times. The halos of large galaxies are filled with the remains of destroyed dwarf galaxies. Streams of stars looping through space are evidence of these ancient meals. In this sense, dwarf galaxies are both survivors and victims of cosmic evolution. So why do some dwarf galaxies end up alone? The answer lies in location and timing. Dwarf galaxies that form in dense regions almost never stay isolated. Gravity pulls them inward. Their paths cross those of larger galaxies. Eventually, they become satellites or are destroyed. But dwarf galaxies that form far from dense regions experience a very different fate. In the emptiest parts of the universe, there are no massive neighbors nearby. No strong gravitational pulls, no frequent encounters. A dwarf galaxy born in such a region can remain alone for billions of years. This is why many isolated galaxies are dwarfs. Their small size allows them to exist quietly without drawing attention. Their weak gravity means they do not easily attract companions. They drift through space, unnoticed, in regions where very little else exists. However, being small also makes isolation dangerous. Dwarf galaxies have weak gravity. This affects everything about their lives. Their gas is loosely held. Their stars move more slowly. Their ability to resist internal and external forces is limited. In crowded environments, this weakness is a disadvantage, but in deep isolation, it can become a strange kind of balance. In empty regions, there are no strong tidal forces trying to tear a dwarf galaxy apart, no hot gas to strip its own gas away, no repeated encounters to disturb its structure. As a result, some dwarf galaxies can survive far longer in isolation than they ever could near a giant galaxy. This survival in emptiness is one of the most fascinating aspects of isolated dwarf galaxies. They are fragile, yet they endure. Many isolated dwarfs show signs of extremely slow evolution. Their star formation rates are low but steady. They form stars over billions of years instead of in violent bursts. Their chemical composition changes slowly. Heavy elements build up gradually as stars live and die. This slow pace preserves early conditions. In crowded regions, dwarf galaxies often lose their gas early and stop forming stars. They become quiet relics shaped by their environment. In isolation, some dwarfs keep their gas and continue forming stars long after similar galaxies elsewhere have gone dark. This makes isolated dwarf galaxies powerful windows into the past. Because they have experienced fewer disturbances, they preserve clues about how the first galaxies formed. Their structure, star, populations and chemistry can reflect conditions that existed when the universe was much younger. In many ways, isolated dwarfs are living fossils. They are not frozen in time, but they evolve slowly enough that traces of the early universe remain visible. Astronomers can study their stars to learn when star formation began, how fast it progressed, and how early galaxies managed their gas. Another important aspect of isolated dwarf galaxies is dark matter. Dwarf galaxies are some of the most dark matter-dominated objects in the universe. Even though they contain relatively few stars, they sit inside dark matter halos that are much more massive than their visible components. This dark matter provides extra gravity, helping them stay together. In isolated environments, these dark matter halos are especially important. Without nearby galaxies to disturb them, the internal balance between dark matter, gas and stars becomes easier to study. Astronomers can measure how stars move inside these galaxies and infer the distribution of dark matter with fewer complications. This is one reason scientists are so interested in isolated dwarfs. They provide clean tests for theories of dark matter. If a dwarf galaxy lives in isolation, its structure reflects internal physics rather than environmental damage. Any strange behavior becomes more meaningful. Isolated dwarf galaxies also challenge some expectations. For a long time, scientists believed that dwarf galaxies in isolation would always be gas-rich and actively forming stars. Without external forces stripping their gas away, they should remain lively. But observations show a more complex picture. Some isolated dwarfs are active, others are surprisingly quiet. This tells us that environment is not the only factor shaping dwarf galaxies. Internal processes matter too. Early bursts of star formation can push gas out of a small galaxy. Radiation from the first stars in the universe may have prevented gas from falling in. Supernova explosions can heat gas enough to escape weak gravitational fields. Even in isolation, a dwarf galaxy can change dramatically. This realization has reshaped how astronomers think about galaxy evolution. Isolation does not guarantee simplicity. Small galaxies can follow many different paths, depending on their initial conditions and early history. Another reason dwarf galaxies dominate isolated populations is simple numbers. There are far more dwarf galaxies than large ones. The universe naturally produces many small galaxies and only a few giants. This means that statistically, if you search deep voids, you're much more likely to find dwarfs than massive spirals. Large galaxies require large amounts of matter. Such matter usually gathers in dense regions. Void environments simply do not have enough material to build giant galaxies easily. Small galaxies, however, can form from modest amounts of gas and dark matter. This makes dwarf galaxies the natural residents of cosmic emptiness. Yet despite their size, their importance cannot be overstated. Dwarf galaxies were likely the first galaxies to form in the universe. Larger galaxies grew later by merging these small systems together. In this sense, dwarf galaxies are the ancestors of everything we see today. Studying isolated dwarf galaxies allows astronomers to study these ancestors without the confusion introduced by billions of years of mergers. They show us how galaxies might look if they were allowed to grow up quietly. They show us how stars formed when the universe was young. They show us how dark matter behaves on small scales. And they show us that even the smallest objects can survive for billions of years in the right conditions. In the vast emptiness of cosmic voids, dwarf galaxies drift silently, barely visible, often ignored. But within them lies a record of cosmic history that cannot be found anywhere else. When astronomers look at galaxies across the universe, one of the first things they notice is shape. Some galaxies have elegant spiral arms winding around bright centers. Others appear smooth and rounded, like glowing clouds. Many look messy, stretched or broken, with long tails of stars pulled out into space. These shapes are not random. They tell the story of what a galaxy has lived through. A galaxy's shape is its history, written in light. To understand how isolation changes a galaxy's shape, we must first understand why galaxies look the way they do in the first place. Shape is not fixed at birth. Galaxies change over time. They respond to gravity, motion, and interaction. In crowded regions, this process is loud and violent. In isolated regions, it is quiet and slow. This difference leaves a clear mark on how galaxies look. Let us begin with the most familiar shape, the spiral galaxy. Spiral galaxies, like the Milky Way, have flat disks with graceful arms, spiraling outward from a central bulge. These arms are rich in gas and dust and are sites of active star formation. Spiral structure requires balance. Rotation must be steady. Gas must be present. Disturbances must be limited. In crowded environments, this balance is hard to maintain. When a spiral galaxy passes close to another galaxy, gravity pulls on it unevenly. One side feels a stronger force than the other. This stretches the galaxy. Arms become distorted. Gas is pulled out. Over time, repeated encounters can destroy the spiral pattern completely. In extreme cases, spiral galaxies lose their structure and become something else. But in isolation, spiral galaxies have a chance to remain calm. An isolated spiral galaxy can rotate undisturbed for billions of years. Its gas settles into a stable disk. Spiral arms persist. Star formation continues along predictable paths. Without close neighbors to interfere, the galaxy evolves gently. This is why some isolated galaxies have remarkably clean, symmetric spiral shapes. They look almost perfect, as if drawn carefully rather than shaped by chaos. Now consider irregular galaxies. Irregular galaxies lack clear structure. They do not have spiral arms or smooth rounded shapes. Their stars and gas appear scattered. For a long time, astronomers believed irregular shapes were the result of interactions and collisions. In many cases, this is true. When galaxies collide or pass close by, gravity disrupts their structure. Gas clouds crash into one another. Star formation becomes chaotic. The result is often an irregular shape, but isolation introduces an interesting twist. Some isolated galaxies are also irregular, even though they have never interacted with another galaxy. This tells us that not all irregularity comes from violence. In isolated environments, irregular shapes often reflect internal processes. Uneven star formation, bursts of activity in one region, and quiet periods in another can give a galaxy a lopsided appearance. Small galaxies, especially dwarfs, may never develop stable disks at all. Their weak gravity cannot organize stars into clean patterns. So isolation does not guarantee symmetry, but it does remove one major source of chaos. This brings us to an important idea: calm evolution. In isolation, galaxies evolve mainly through internal processes. Stars form from gas clouds. Supernova explosions enrich the surrounding gas with heavy elements. Over time, star formation slows as gas is used up or heated. These changes happen gradually. There are no sudden disruptions, no tidal shocks, no violent rearrangements of stars. The galaxy ages the way a quiet village ages, not the way a city changes during war. In crowded environments, galaxies are constantly pulled and stretched by neighbors. This effect is known as tidal stretching. Tidal forces occur because gravity is stronger on the side of a galaxy closer to another massive object. This difference in pull stretches the galaxy, sometimes dramatically. Long streams of stars can be pulled out, forming glowing tails that extend far into space. These features are beautiful, but they are signs of disturbance. Isolated galaxies rarely show such features. Without nearby massive neighbors, there are no strong tidal forces to distort them. Their stars remain bound. Their gas stays where it is. Their structure remains intact. This lack of tidal stretching allows galaxies to maintain simpler, cleaner shapes for much longer periods. Another major factor shaping galaxies is violent mergers. When galaxies merge, the result is dramatic. Disks are destroyed. Orbits of stars become random. Gas falls toward the center, triggering intense bursts of star formation. Over time, the merged galaxy often becomes smooth and rounded, losing any spiral structure it once had. Many elliptical galaxies are believed to be the result of multiple mergers. In isolation, mergers are rare or non-existent. An isolated galaxy is unlikely to encounter another galaxy close enough to merge. Even if there are distant neighbors, cosmic expansion and weak gravity prevent close approaches. As a result, isolated galaxies avoid one of the most powerful forces of change in the universe. This has profound effects on how they age. Without mergers, isolated galaxies do not experience sudden growth spurts. Their mass increases slowly. Their star populations remain relatively ordered. Their internal motions stay more predictable. This leads to what we might call peaceful aging. Galaxies age in isolation, much like a calm landscape changes over time. Stars are born, stars die, gas slowly changes. The overall structure remains recognizable. In contrast, galaxies in crowded regions age like cities under constant construction and conflict. Their structure is torn down and rebuilt again and again. Peaceful aging also affects a galaxy's appearance in color and brightness. Isolated galaxies often show gradual changes in color. As star formation slowly declines, bright blue stars become less common. Older, redder stars dominate. This transition happens smoothly, not suddenly. In crowded environments, star formation can shut down abruptly due to gas stripping or heating. Galaxies can change color quickly, becoming red and inactive in a relatively short time. Isolation allows for a more extended middle age. Another subtle effect of isolation is symmetry. Without external forces pulling unevenly on a galaxy, its shape can remain more balanced. Many isolated galaxies show a high degree of symmetry, especially in their outer regions. Their disks are smooth. Their edges are clean. Their light fades evenly. This symmetry makes isolated galaxies visually striking in a quiet way. They do not look dramatic or violent, they look settled. However, it is important to remember that isolation does not freeze a galaxy in time. Internal processes still matter. Bars can form in spiral galaxies, redistributing stars and gas. Star formation can occur unevenly. Supernova explosions can reshape local regions. Over billions of years, even an isolated galaxy will change. but the key difference is pace. Isolation slows everything down. This slower pace gives astronomers a unique opportunity. By studying isolated galaxies, scientists can observe how galaxies evolve when left largely alone. They can separate the effects of internal physics from external influence. This helps answer fundamental questions. What shape does a galaxy naturally tend toward? How long can spiral structure survive? How does star formation decline without outside interference? How stable are disks over cosmic time? Isolated galaxies provide the clearest answers. They show us what galaxies might look like if the universe were quieter, if gravity did not constantly force interactions, if growth came from patience rather than violence. In this sense, isolated galaxies represent an alternate version of cosmic history, a universe where change happens slowly, a universe where shape is preserved, a universe where galaxies grow old without being torn apart. At the heart of every galaxy lies the same basic question: how are stars born and what controls the rhythm of their birth? In crowded regions of the universe, the answer is often loud and dramatic. In isolated galaxies, the answer is quiet, slow, and deeply revealing. To understand star formation in lonely galaxies, we must begin with the basics. Stars are born from gas. Every star begins its life inside a cloud of cold gas and dust, mostly hydrogen. These clouds drift through a galaxy, invisible to our eyes but massive in size. Over time, gravity pulls parts of these clouds together. As gas becomes denser, it heats up. Eventually, the core becomes hot enough for nuclear fusion to begin. A star is born. This process is universal. It happens in every galaxy, everywhere in the universe. But the speed, efficiency, and style of star formation depend heavily on environment. In crowded regions of space, star formation is often triggered by interaction. When galaxies pass close to one another or collide, their gas clouds are compressed. Shock waves travel through gas. Clouds collapse rapidly. This leads to bursts of star formation, where thousands or even millions of stars are born in a relatively short time. These starbursts make galaxies shine brightly. They fill space with blue light from young, massive stars, but they are short-lived. Once the gas is consumed or heated, star formation drops sharply. Lonely galaxies experience something very different. In isolated galaxies, there are no close neighbors to disturb gas clouds, no tidal forces to compress them, no collisions to trigger sudden collapse. Gas clouds are left alone to evolve on their own. This changes everything. Without external triggers, star formation becomes a slow and steady process. Gas clouds collapse only when internal conditions are right. Gravity works quietly. Turbulence fades. Pressure balances itself slowly. As a result, isolated galaxies often form stars at a much lower rate than galaxies in crowded regions. This does not mean they stop forming stars. It means they form stars patiently. In many isolated galaxies, especially dwarfs, star formation continues for billions of years at a gentle pace. Instead of burning bright and fast, these galaxies glow softly and steadily. This slow pace has important consequences. First, gas lasts longer. In crowded galaxies, gas is often consumed quickly during starbursts or stripped away by interactions. In isolation, gas clouds can survive for extremely long periods. They're not torn apart, they're not heated by violent events, they drift quietly through the galaxy, waiting. Some gas clouds in isolated galaxies may survive for billions of years before forming stars. This leads to long-lived gas reservoirs. These reservoirs act like savings accounts rather than spending sprees. Star formation happens gradually, allowing galaxies to sustain themselves over long cosmic timescales. Second, star formation becomes more uneven. In isolated galaxies, star formation often happens in small pockets rather than across the entire galaxy. A single gas cloud may collapse and form stars, while nearby regions remain quiet. Over time, star-forming regions move slowly through the galaxy as conditions change. This creates a patchy appearance. Some isolated galaxies show bright star-forming regions surrounded by large, dark areas. Others show faint star formation spread thinly across their disks. Third, the stars themselves are different. Because star formation is slow, isolated galaxies tend to produce fewer massive stars at any given time. Massive stars burn brightly but live short lives. They dominate the light of active galaxies. When they die, they explode as supernova, injecting energy into their surroundings. In isolated galaxies, fewer massive stars mean fewer supernova. This keeps the environment calmer. Gas clouds are not constantly disrupted by explosions. Star formation proceeds without being shut down or restarted violently. This creates a self-regulating system where stars form gently and predictably. Over time, this leads to galaxies that are dim but steady. They do not shine as brightly as starburst galaxies. They do not dominate telescope images, but their light persists. It changes slowly. It tells a story of endurance rather than drama. Another key difference in lonely galaxies is chemical evolution. When stars die, they enrich their surroundings with heavier elements like carbon, oxygen, and iron. In galaxies with rapid star formation, this enrichment happens quickly. Gas becomes metal-rich early in the galaxy's life. In isolated galaxies with slow star formation, chemical enrichment is gradual. Heavy elements build up slowly over billions of years. As a result, stars in isolated galaxies often have lower metallicity, meaning they contain fewer heavy elements. This is important because it connects isolated galaxies to the early universe. The first stars formed from nearly pure hydrogen and helium. Over time, galaxies became richer in heavier elements. Isolated galaxies preserve a record of this gradual process. By studying their stars, astronomers can learn how chemical evolution unfolds when left largely undisturbed. Isolation also affects how star formation ends. In crowded environments, star formation often stops abruptly. Gas is stripped away or heated beyond the point where it can collapse. A galaxy may go from active to quiet in a relatively short time. In isolation, star formation fades slowly. As gas is used up, star formation gradually declines. There is no sudden shutdown. The galaxy enters old age gently, with fewer and fewer new stars forming. This creates a smooth transition rather than a sharp break. Some isolated galaxies may continue forming stars at low levels even today, billions of years after their formation. Others may have slowed almost to a stop, glowing softly with the light of old stars. This gentle decline makes isolated galaxies excellent laboratories for studying long-term star formation. Astronomers can observe galaxies at different stages of slow aging and piece together how star formation evolves over time without external influence. There is also an emotional side to this story. When we imagine star formation, we often think of violence and brilliance, explosions, bright nebulae, dramatic change. But isolated galaxies remind us that creation does not always need chaos. Stars can be born quietly. They can form in silence without collisions or shocks. They can light up their surroundings gently, contributing to a steady glow that lasts for billions of years. This quiet mode of star formation may have been common in the early universe, before large structures fully formed. By studying lonely galaxies today, we may be seeing echoes of that ancient rhythm. Another fascinating aspect is stability. In isolated galaxies, star formation feedback is often weaker. This means that gas clouds are not constantly blown apart by stellar winds and explosions. This stability allows gas to settle into long-lived structures. Some isolated galaxies show rotating disks of gas that remain stable for billions of years. These disks slowly convert gas into stars without dramatic disruption. This stability contrasts sharply with galaxies in clusters, where gas disks are often distorted, truncated, or destroyed. Finally, isolated galaxies teach us an important lesson about brightness and importance. In astronomy, brightness often attracts attention. The brightest objects dominate images and headlines, but brightness does not equal significance. Isolated galaxies may be faint, but they are crucial. They show us how galaxies behave when left alone. They reveal the slow side of cosmic evolution. They preserve conditions that crowded galaxies have long lost. Their dim light is not a sign of weakness. It is a sign of patience. To understand isolated galaxies fully, we must talk about something we cannot see at all. Something that does not glow, does not reflect light, and does not emit energy in any direct way. And yet it shapes everything. It holds galaxies together. It guides their motion. It determines where galaxies form and how they evolve. This invisible substance is called dark matter. Dark matter is one of the most important ideas in modern astronomy, and isolated galaxies are some of the best places in the universe to study it. Let us start with a simple explanation. When astronomers observe galaxies, they measure how fast stars move inside them. According to normal physics, stars farther from the center of a galaxy should move more slowly because there is less visible matter pulling on them. But when scientists actually measure these speeds, they find something surprising. Stars far from the center move just as fast as stars closer in. This should not be possible if galaxies contained only the stars, gas, and dust we can see. There must be extra mass providing extra gravity, mass that does not shine. That mass is dark matter. Dark matter makes up most of the mass in galaxies. In fact, for many galaxies, especially dwarf galaxies, dark matter outweighs visible matter by a huge margin. Without dark matter, galaxies would fly apart. They would not hold together long enough to form stars or develop structure. So every galaxy lives inside a dark matter halo. This halo is much larger than the visible galaxy. It extends far beyond the stars, forming a vast invisible sphere of gravity. Galaxies move inside these halos like boats floating inside a deep, unseen ocean. Now, here is where isolation becomes incredibly important. In crowded regions of the universe, galaxies interact constantly. Their dark matter halos overlap. Gravity from nearby galaxies disturbs motions. Mergers mix everything together. This makes it very difficult to study dark matter cleanly. But isolated galaxies are different. An isolated galaxy sits alone in space. Its dark matter halo is not being pulled or distorted by nearby halos. There are no close neighbors adding extra gravitational forces. The galaxy's motion is shaped almost entirely by its own dark matter and its own visible matter. This creates what scientists call a clean gravity environment. In such an environment, astronomers can study how stars move and directly connect those motions to the underlying dark matter distribution. There are fewer unknowns, fewer complications, fewer assumptions. This is why isolated galaxies are often described as natural laboratories for dark matter research. Dwarf galaxies are especially valuable in this role. As we discussed earlier, dwarf galaxies contain relatively few stars but large amounts of dark matter. In some dwarfs, dark matter dominates the galaxy's mass almost completely. This makes the influence of dark matter easier to detect and measure. In isolated dwarf galaxies, the situation becomes even clearer. There are no tidal forces from massive neighbors stretching the galaxy. There is no gas stripping altering its structure. What astronomers observe is close to the galaxy's natural state. By measuring how stars move in these galaxies, scientists can map the dark matter halo and test different theories about its nature. This leads to some of the most important questions in modern physics. What exactly is dark matter made of? Is it made of unknown particles? Does it interact only through gravity? Does it behave the same way everywhere in the universe? Isolated galaxies help answer these questions. For example, Different dark matter models predict different density patterns inside galaxies. Some models suggest that dark matter forms a sharp peak at the center of a galaxy. Others predict a more spread-out distribution. In crowded environments, interactions can blur these patterns. In isolation, the original structure is more likely to remain intact. When astronomers study isolated dwarf galaxies, they sometimes find results that challenge existing models. In some cases, the dark matter appears less concentrated than expected. In others, it behaves exactly as predicted. Each observation helps refine our understanding. Isolated galaxies also help test ideas about galaxy formation itself. According to current models, galaxies form inside dark matter halos. Gas falls into these halos, cools, and forms stars. The size and shape of the dark matter halo influence the galaxy's structure. By studying isolated galaxies, astronomers can see how this process unfolds without interference. Does a certain type of dark matter halo always produce a certain type of galaxy? How does star formation affect the dark matter distribution over time? Can stars push dark matter around through repeated explosions and energy release? These questions are difficult to answer in crowded environments. In isolation, the answers become clearer. Another powerful use of isolated galaxies is in testing cosmic models. Modern cosmology relies on simulations. Scientists create computer models of the universe based on known laws of physics and assumptions about dark matter and dark energy. These simulations predict how galaxies should form and where they should be located. One key prediction is the number of small galaxies in different environments. Some models predict many more dwarf galaxies than we observe. This mismatch is known as the missing satellites problem. Isolated galaxies play a crucial role here. If isolated dwarf galaxies are missing, it could mean our understanding of dark matter is incomplete. If they exist but are difficult to detect, it may point to observational limits rather than theoretical flaws. By searching voids and studying isolated dwarfs, astronomers test whether models match reality. Isolated galaxies also help study dark matter interactions. Some theories suggest that dark matter particles may interact with each other slightly, not just through gravity. These interactions could affect how dark matter spreads inside galaxies. Crowded environments mask these effects. Isolated galaxies with fewer disturbances offer a cleaner view. If dark matter behaves differently in isolation than predicted, it could point to new physics. This is why even a single isolated galaxy can have a huge impact on science. One quiet dwarf drifting alone in a void can challenge decades of theory. Another important advantage of isolated galaxies is stability. Because they evolve slowly, isolated galaxies preserve their dark matter structure over long periods. In crowded regions, repeated interactions can heat dark matter, change its distribution, or strip parts of the halo away. In isolation, these effects are minimal. This makes isolated galaxies excellent benchmarks. Astronomers can compare them across different distances and ages to see whether dark matter behaves consistently across the universe. So far, observations suggest remarkable consistency. Dark matter appears to behave the same way in isolated galaxies as it does in clusters, supporting the idea that it is a fundamental component of the universe. Yet mysteries remain. Despite decades of study, dark matter has never been directly detected in laboratories on Earth. All our knowledge comes from its gravitational effects. Isolated galaxies provide some of the strongest evidence that dark matter exists and dominates cosmic structure. Without dark matter, isolated galaxies could not survive. Their stars would drift apart, their gas would escape, their quiet existence over billions of years would be impossible. In this way, isolation highlights the importance of the invisible. It reminds us that what we cannot see often matters more than what we can. When scientists describe isolated galaxies, one phrase appears again and again: time capsules. It is a powerful idea. A time capsule is something sealed away from change, preserved so that it carries information from another era. In many ways, isolated galaxies fit this description better than almost any other object in the universe. But are they truly frozen in time? Or is the reality more subtle? To answer this, we must think carefully about what time means on cosmic scales and how change happens in the universe. Galaxies are not static objects. They are alive with motion. Stars orbit their centers. Gas flows and collapses. Stars are born and die. Even the quietest galaxy is constantly evolving. So when astronomers talk about galaxies being frozen in time, they do not mean that nothing happens. What they mean is something more specific. They mean that isolated galaxies change slowly, and that many of the violent events that reshape galaxies elsewhere never happen to them. As a result, these galaxies preserve conditions that disappeared long ago in crowded regions of the universe. In this sense, isolated galaxies are not perfectly frozen, but they are remarkably well preserved. To understand why this matters, we need to return to the early universe. In the first few billion years after the Big Bang, the universe looked very different from what we see today. Galaxies were smaller, gas was more abundant, heavy elements were rare, interactions were less common in some regions and more intense in others. Over time, galaxies collided, merged and grew. Star formation surged and declined. Gas was consumed, heated, or stripped away. The universe became more structured, more complex, and in many ways, more violent. Most galaxies today carry scars from this long history. Spiral arms warped by encounters, elliptical shapes formed by mergers, chemical compositions altered by repeated generations of stars. These features make it difficult to reconstruct what galaxies were like in the early universe. Isolation changes this story. An isolated galaxy avoids many of these disruptive events. It does not experience frequent mergers. It is not stretched by strong tidal forces. It is not stripped of gas by hot cluster environments. As a result, its internal structure and composition remain closer to their original state. This is what makes isolated galaxies feel like time capsules. They preserve early universe conditions better than most galaxies. For example, many isolated galaxies have low metallicity, meaning their stars contain relatively few heavy elements. This is similar to the chemical conditions that existed when the universe was young. Studying these stars allows astronomers to understand how early generations of stars formed and evolved. In crowded regions, chemical enrichment happens quickly. Gas is processed through many generations of stars. Heavy elements build up rapidly. The original chemical signature is lost. In isolation, this process is slower. Some isolated galaxies still contain stars that formed billions of years ago from nearly pristine gas. These stars act as direct messengers from the early universe. Another way isolated galaxies preserve the past is through minimal disturbance. In a crowded environment, galaxies are constantly reshaped by gravity. Even distant encounters can alter orbits, redistribute stars, and change structure. Over billions of years, these effects accumulate. In isolation, these disturbances are absent or extremely rare. Stars follow stable orbits for long periods. Gas settles into calm configurations. Internal processes dominate evolution. This stability allows astronomers to study galaxies as systems governed primarily by their original conditions. This is incredibly valuable for science. Imagine trying to understand how a machine works while it's being constantly hit, pulled apart, and reassembled. That is what studying galaxies in clusters can be like. Isolated galaxies, by contrast, are like machines left running undisturbed. Their behavior reveals underlying rules more clearly. This is one reason astronomers love studying isolated galaxies. They offer clarity. When astronomers observe an isolated galaxy, they can make simpler assumptions. If a galaxy has an unusual shape, star formation pattern, or dark matter distribution, it is more likely to be the result of internal physics rather than recent interactions. This reduces uncertainty. For example, if a galaxy shows slow star formation, astronomers do not have to wonder whether gas was stripped away by a neighbor. If a galaxy has a smooth shape, they do not have to consider whether it was recently disturbed by a merger. Isolation removes many variables. This makes isolated galaxies ideal test cases for theories of galaxy formation and evolution. Scientists use them to answer fundamental questions. How does star formation proceed when left alone? How do galaxies age naturally? How does dark matter shape galaxies over long periods without interference? What was the baseline state of galaxies before interactions became common? These questions are difficult to answer using crowded galaxies alone. Another powerful aspect of isolated galaxies as time capsules is comparative study. Astronomers can compare isolated galaxies of different masses, ages, and environments to build a timeline of evolution. By studying galaxies that are isolated but formed at different times, scientists can reconstruct how galaxies change naturally over cosmic history. This is like having multiple time capsules from different eras. Each one reveals a snapshot of a different stage in cosmic evolution. Isolated galaxies also help bridge the gap between the early universe and the present. Observing distant galaxies allows astronomers to look back in time because light takes time to travel. But distant galaxies are faint and hard to study in detail. Isolated galaxies nearby offer a complementary approach. They are close enough for detailed observation, but quiet enough to resemble early systems. In this way, isolated galaxies act as local analogues of early galaxies. They allow astronomers to test ideas about the early universe using nearby objects that can be studied in much greater detail. This is incredibly powerful. For example, by studying star formation in isolated dwarf galaxies today, scientists can infer how star formation might have proceeded in the first galaxies. By studying their chemical evolution, they can understand how the first heavy elements were produced and distributed. This connection between isolation and the past is not perfect, but it is strong. It also challenges some assumptions. For a long time, scientists believed that early galaxies were always chaotic and violent, but isolated galaxies show that calm evolution has always been possible. Even in the early universe, some regions were quiet, some galaxies grew slowly, some avoided interactions. This suggests that the early universe was more diverse than once thought. Not all galaxies followed the same path. Another reason isolated galaxies are so valuable is that they help test the limits of our theories. If a theory predicts that certain types of galaxies should not exist in isolation, and yet they do, the theory must be revised. Isolated galaxies often sit at the edge of what models predict. They are exceptions that force deeper understanding, and yet it is important to be careful. Isolated galaxies are not perfect time capsules. They still evolve. They still change. Internal processes can reshape them significantly over billions of years. Supernova explosions, stellar winds, and gradual gas loss all leave their mark. Isolation slows evolution, but it does not stop it. So rather than thinking of isolated galaxies as frozen snapshots, it is better to think of them as slow-motion records. They show us evolution at a pace that can be followed and understood. They reveal processes that are hidden in faster, more chaotic systems. They are quiet storytellers. In a universe shaped by gravity and time, isolation creates memory. It allows galaxies to carry traces of their origins far into the future. When astronomers study isolated galaxies, they are not just studying lonely objects. They are studying the universe remembering itself. When we talk about life in the universe, we usually focus on planets, stars, and solar systems. We ask whether a planet has water, whether its star is stable, or whether its atmosphere can protect life. These are important questions. But there is a much larger scale that is often ignored: the galactic environment itself. Galaxies are not just collections of stars. They are environments that shape radiation levels, star behavior, and long-term stability. Over billions of years, these factors can influence whether life has a chance to appear and survive. So this leads to a fascinating question. Can life exist near isolated galaxies? At first, the idea sounds strange. Isolated galaxies are lonely, quiet, and far from everything else. But loneliness does not automatically mean hostility. In fact, in some ways, isolation might create some of the calmest environments in the universe. To explore this idea, we need to think about habitability on cosmic scales. Habitability is often discussed on the scale of planets, but life is affected by much larger forces. Supernova explosions can flood regions with deadly radiation. Galaxy collisions can trigger intense starbursts that fill space with high-energy particles. Active black holes can blast radiation across entire galaxies. Where a star system lives inside a galaxy matters, and where a galaxy lives in the universe may matter too. Let us begin with star stability, one of the most important factors for life. Life, as we understand it, needs time. It takes millions, even billions of years for life to develop complexity. This requires stars that burn steadily for long periods, stars that explode too soon or vary wildly in brightness, make life difficult. In isolated galaxies, star formation tends to be slow and gentle. There are fewer bursts of massive star formation. This means fewer massive stars that explode as supernovae. It also means a higher proportion of long-lived stable stars, like red dwarfs and sun-like stars. These stars can shine for billions or even trillions of years. This long-term stability is good for life. In crowded galaxies or clusters, star formation can be chaotic. Interactions can trigger waves of massive star birth, followed by waves of supernova explosions. These events flood nearby regions with radiation that can strip atmospheres and damage developing life. In isolated galaxies, these violent cycles are much less common. Stars form slowly. Supernova are rarer and more spread out in time. This creates a calmer stellar environment where planetary systems are less likely to be sterilized repeatedly. Next, we must consider the radiation environment. Radiation is one of the biggest threats to life on cosmic scales. High-energy radiation from supernova, gamma-ray bursts, and active galactic nuclei can damage DNA, destroy atmospheres, and make planets uninhabitable. Crowded regions of the universe are dangerous places. In dense galaxy clusters, galaxies are packed closely together. Supernova rates are high. Interactions can feed supermassive black holes, causing them to become active and emit powerful radiation jets. Cosmic rays fill space at high levels. In isolated galaxies, many of these dangers are reduced. There are fewer nearby galaxies, which means fewer external radiation sources. If a supernova explodes in a distant galaxy, its radiation weakens greatly before reaching an isolated galaxy millions of light years away. Isolation acts like distance-based shielding. Inside the galaxy itself, the slow pace of star formation means fewer massive stars and fewer supernovae. Radiation levels are generally lower and more stable over time. This does not mean isolated galaxies are radiation-free. Supernovae still occur, stars still emit radiation, but the overall environment is calmer. This calmness could be beneficial for life. Another factor is galactic collisions. When galaxies collide or pass close to each other, gravity disrupts star orbits. Comets and asteroids can be knocked from stable paths, increasing impact rates on planets. Radiation levels rise, gas clouds collapse rapidly, creating waves of massive stars and explosions. These events can be catastrophic for life. Isolated galaxies avoid these events entirely. No close encounters, no mergers, no sudden bursts of chaos. Planetary systems can remain stable for extremely long periods. This long-term stability is one of the strongest arguments in favor of habitability near isolated galaxies. But isolation also has drawbacks. Life requires more than stability. It requires raw materials. Heavy elements like carbon, oxygen, nitrogen, iron, and phosphorus are essential for life as we know it. These elements are created inside stars and spread through space when stars die. In isolated galaxies, star formation is slower. Fewer stars are born and die over time. This means chemical enrichment happens more slowly. As a result, isolated galaxies often have lower metallicity, meaning fewer heavy elements. This could make planet formation more difficult. Rocky planets like Earth require heavy elements. If a galaxy has very low metallicity, it may produce fewer rocky planets and more gas-dominated systems. This could reduce the chances of Earth-like worlds forming. So isolation presents a trade-off. On one hand, it offers calm, stable environments with low radiation. On the other hand, it may limit the availability of the materials needed for complex chemistry and life. Another consideration is planetary system diversity. In regions with ongoing star formation and enrichment, new generations of stars form with higher metallicity. Over time, the universe becomes better at making planets. In isolated galaxies, this process is slower. Planet formation may still occur, but the range of planet types could be narrower. However, slower does not mean impossible. Even low metallicity environments can form rocky planets. Observations in our own galaxy show that planets exist around stars with a wide range of metallicities. Life may not require Earth-like conditions exactly as we know them. This opens the possibility that life near isolated galaxies could be different but still viable. There is also the question of time. Isolated galaxies evolve slowly. This means they can remain habitable for extremely long periods. While star formation may be slow, it can continue steadily for billions of years. Life might take longer to appear, but once it does, it may have more time to evolve. In crowded galaxies, frequent disruptions could reset the clock repeatedly. In isolation, the clock may run uninterrupted. This leads to a powerful idea. Isolation may reduce the chance of life starting, but increase the chance of life surviving once it begins. Now consider the idea of a quiet universe for life. Human history shows that stability matters. Civilizations grow during long periods of relative calm. Life on Earth benefited from long stretches without major extinction-level events. On cosmic scales, isolated galaxies may provide similar calm. They are not exciting, they do not blaze with activity, but they offer consistency. A planet orbiting a stable star inside a quiet galaxy, far from violent cosmic events, might enjoy billions of years of uninterrupted evolution. This could allow life to become complex, intelligent, and perhaps even technological. Of course, this is still speculation. We have no direct evidence of life beyond Earth. We do not yet know how common life is, or what conditions it truly requires. But thinking about isolated galaxies expands our imagination. It reminds us that habitability is not just about stars and planets, it is about context. Life does not exist in isolation from the universe. It is shaped by everything around it, from nearby stars to the structure of the cosmos itself. Isolated galaxies offer one of the calmest contexts possible. They may not be the most fertile places for life to begin, but they may be among the safest places for life to endure. In the end, isolation is neither good nor bad. It is a different path, a path of patience instead of violence, of stability instead of chaos, of long, quiet stretches of time. If life exists near isolated galaxies, it may be rare, slow to emerge, and profoundly ancient. And if such life looks up at its night sky, it may see very little. Few neighboring galaxies, few cosmic lights, just darkness and silence, a quiet universe. If isolated galaxies are so important, a natural question follows. Why did it take so long to find them? And why do astronomers believe that many more are still hidden, waiting to be discovered? The answer is simple and humbling. Most isolated galaxies are almost invisible. They are faint, they are small, they live far away from bright cosmic landmarks. They do not sit inside crowded clusters that draw attention. They do not glow with intense star formation. Many of them emit very little light at all. Finding them is one of the hardest challenges in modern astronomy. To understand how scientists detect these elusive objects, we need to look at the tools they use, the strategies they follow, and the limitations they face. Let us start with telescopes and surveys. Astronomers do not discover galaxies one by chance. They rely on large sky surveys, systematic efforts to map huge portions of the sky in detail. These surveys scan the heavens night after night, collecting light from millions or even billions of objects. Early surveys focused mainly on visible light. They captured the bright galaxies easily. Spirals, ellipticals, and clusters stood out clearly. But isolated galaxies often slipped through the cracks. Why? Because many isolated galaxies are low surface brightness galaxies. This means their light is spread thinly across a wide area. Even if the total amount of light is significant, it is so diffuse that it blends into the background darkness. To early telescopes, these galaxies looked like faint smudges or noise. Modern surveys use far more sensitive detectors. They can collect light over long periods, stacking faint signals together to reveal objects that were previously invisible. Digital imaging has transformed this field, allowing astronomers to process data in ways that were impossible in the past. But visible light alone is not enough. Many isolated galaxies do not shine brightly in visible wavelengths. Their stars are old and faint. Their star formation is weak. To find them, astronomers must look beyond what the human eye can see. This is where infrared detection becomes crucial. Infrared light reveals cooler objects. Older stars emit more infrared than visible light. Dust that blocks visible light often glows in the infrared. For isolated galaxies with old stellar populations, infrared surveys can be far more effective than optical ones. Space-based telescopes are especially important here. Earth's atmosphere absorbs much of the infrared light coming from space. By placing telescopes above the atmosphere, astronomers gain a much clearer view. Infrared surveys have revealed entire populations of galaxies that were nearly invisible before. Some isolated galaxies only became obvious when viewed in these wavelengths, but even infrared light does not tell the whole story. Another powerful method for finding isolated galaxies involves radio astronomy, especially the detection of hydrogen gas. Most galaxies contain hydrogen gas, the raw material for star formation. This gas emits a specific radio signal known as the 21 centimeter line. Radio telescopes can detect this signal even when a galaxy has very few stars. This technique has been revolutionary. A galaxy might be almost invisible in visible and infrared light, but still contain large amounts of hydrogen gas. Radio surveys can detect these gas-rich galaxies even in deep voids. This has led to the discovery of isolated galaxies that would otherwise have been completely missed. Radio observations also provide crucial information about distance and motion. By measuring how the hydrogen signal is shifted due to the expansion of the universe, astronomers can estimate how far away a galaxy is and how it is moving. This helps confirm whether a galaxy is truly isolated or simply appears isolated from our point of view. Another important technique is mapping emptiness itself. Astronomers do not only search for galaxies, they also map where galaxies are not. Large-scale surveys allow scientists to create three-dimensional maps of the universe. These maps show filaments, clusters, and voids. By identifying vast empty regions, astronomers can focus their searches inside them. This approach is strategic. Instead of scanning the entire sky equally, astronomers concentrate on known voids, where isolated galaxies are most likely to be found. Deep observations are made in these regions, sometimes focusing on a small patch of sky for weeks or months. Even then, discoveries are rare. Isolated galaxies are spread across enormous volumes of space. They are separated by millions of light years. The chance of finding one in a small field of view is low. This brings us to the challenges of deep space observation. First, distance. Even nearby isolated galaxies can be millions of light years away. Their light is weak by the time it reaches Earth. Detecting it requires long exposure times and extremely sensitive instruments. Second, background noise. The universe is filled with faint light from distant galaxies, stars, and dust. Earth itself adds noise through atmospheric glow and artificial light pollution. Separating a faint galaxy from this background is incredibly difficult. Third, confusion with foreground objects. A faint isolated galaxy may appear similar to a distant star or a small background galaxy. Distinguishing between these requires careful analysis of motion, color, and spectral properties. Fourth, bias. Astronomy has a long history of bias toward bright, easy-to-detect objects. Even today, surveys are more complete for bright galaxies than faint ones. This means our current catalogues are incomplete. Isolated galaxies are often victims of this bias. Another major challenge is time. Deep surveys require long observation times. Telescope time is limited and highly competitive. Observing a single patch of sky deeply enough to detect faint isolated galaxies can take many nights. This limits how much of the sky can be studied in this way. As a result, many void regions remain poorly explored. This leads to an important conclusion. Many isolated galaxies are still undiscovered. Astronomers are confident of this. Computer simulations predict far more small, isolated galaxies than we have observed. The gap between prediction and observation suggests that many galaxies are simply too faint to detect with current technology. Some may contain very few stars, others may be dominated by dark matter, with almost no visible matter at all. These objects would be nearly impossible to detect except through their gravitational effects. There is also the possibility of ultra-diffuse galaxies, objects with sizes similar to large galaxies but extremely low brightness. In isolation, such galaxies could exist quietly, unnoticed. New telescopes are changing this picture. Upcoming surveys will map the sky with unprecedented depth and precision. They will detect fainter objects, measure distances more accurately, and reveal structures that were previously hidden. Each improvement brings new discoveries. As technology advances, astronomers expect to uncover entire populations of isolated galaxies that we have never seen before. Some may challenge existing theories, others may confirm long-standing predictions. Every new isolated galaxy adds a piece to the cosmic puzzle. It tells us about galaxy formation, dark matter, star formation, and the structure of the universe itself. But perhaps the most important lesson is this. The universe is not only defined by what we see, it is defined by what hides in darkness. Isolated galaxies remind us that emptiness is not empty, that silence holds information, that some of the most important objects in the universe do not announce themselves loudly. They wait quietly, far from everything else, until our tools become sensitive enough to notice them. To understand the future of isolated galaxies, we must think in timescales far beyond human history. Not thousands of years, not millions, but billions and trillions of years. On these scales, even galaxies change slowly, and the universe itself becomes the dominant force shaping their fate. Isolated galaxies already live quiet lives, but the future promises something even more extreme. Greater separation, deeper silence, and eventually fading light. Let us begin with what happens to an isolated galaxy over billions of years. Inside an isolated galaxy, evolution continues, but at a gentle pace. Stars are born slowly from remaining gas clouds. Old stars age and die. Massive stars explode as supernova, enriching the surrounding gas with heavier elements. Over time, however, the galaxy's gas supply is gradually depleted. Unlike galaxies in crowded regions, isolated galaxies cannot easily gain new gas. There are no close neighbors to steal material from. No mergers to deliver fresh supplies. What the galaxy begins with is mostly what it must live on. As billions of years pass, star formation steadily declines. Gas clouds become thinner. Star-forming regions grow rarer. The galaxy's light shifts toward redder wavelengths as young blue stars become scarce. What remains is a population dominated by long-lived, low-mass stars. The galaxy grows older, quieter, and dimmer. This process is not sudden. It unfolds slowly over enormous stretches of time. An isolated galaxy may continue forming stars at a low level for tens of billions of years, far longer than galaxies in dense clusters where star formation can be shut down early. In this sense, isolation extends a galaxy's life, but eventually even isolated galaxies run out of fuel. When gas becomes too sparse or too hot to collapse, star formation effectively ends. The galaxy enters a long twilight phase, shining only with the light of aging stars. Now we must ask an important question. Will isolated galaxies ever meet others in the future? The intuitive answer might be yes. Gravity pulls things together after all. Over time, galaxies should drift toward each other and merge. But the universe has another plan. The universe is expanding. This expansion is not just galaxies moving through space. It is space itself stretching. Distances between distant galaxies increase over time. And this expansion is not slowing down. It is accelerating. This acceleration is driven by dark energy, a mysterious force that dominates the universe on the largest scales. For isolated galaxies, this has profound consequences. In dense regions, gravity can overcome expansion. Galaxies in groups and clusters remain bound. They collide and merge despite the universe expanding around them. In low-density regions, gravity is too weak. Isolated galaxies live in exactly these low-density environments. The gravitational pull between them and distant galaxies is small. As the universe expands, these galaxies are carried farther apart. Over time, the expansion wins. This means that most isolated galaxies will never meet another galaxy again. Even if there are distant neighbors today, the space between them will stretch faster than gravity can pull them together. The chance of future interactions decreases with time, not increases. In the far future, each isolated galaxy becomes an island universe. From within that galaxy, all other galaxies will gradually fade from view. Their light will redshift, stretching to longer wavelengths until it becomes undetectable. Eventually, they will disappear beyond the cosmic horizon. For any future observers living in an isolated galaxy, the universe will appear empty. This is ultimate loneliness on a cosmic scale. The galaxy will not only be isolated physically, but also observationally. It will be surrounded by darkness, with no visible evidence of other galaxies. This has deep implications. Future civilizations in such galaxies would have no way of knowing that other galaxies ever existed. They would see only their own stars. The cosmic web would be invisible to them. The universe would look small. Ironically, this is similar to how the universe once appeared to humans before modern astronomy. We once believed the Milky Way was the entire universe. In the far future, that belief would again be reasonable, but for a very different reason. Now consider what happens inside the isolated galaxy itself as time marches on. Stars continue to age. Massive stars die first, within millions of years. Sun-like stars last billions of years. Small red dwarf stars can burn for trillions of years, far longer than the current age of the universe. In isolated galaxies, red dwarfs will dominate the future. These stars shine faintly but steadily. They provide a long-lasting source of light and energy. If life exists around such stars, it may have immense amounts of time to evolve. However, even red dwarfs are not eternal. Eventually, star formation stops completely. Stars age and die without replacement. White dwarfs, neutron stars, and black holes accumulate. The galaxy becomes darker. Its light output declines steadily, as fewer stars shine brightly. Over immense timescales, even the smallest stars fade. This leads us to the idea of a fading future. Isolated galaxies will not end in dramatic explosions. There will be no final collision, no grand merger, no violent transformation. Their end is quiet, a slow dimming, a gradual loss of light. As the universe continues to expand, isolated galaxies drift farther apart from everything else. Inside them, stars die one by one. Black holes may slowly evaporate through Hawking radiation over unimaginably long timescales. Eventually, even the galaxy itself becomes a collection of cold remnants. Planets wander through darkness. Stellar corpses orbit silently. Time stretches on with little change. This future may sound bleak, but it carries an important lesson. Isolation leads to stability, but also to finality. Galaxies that interact grow and change. They recycle material. They create new generations of stars. They remain dynamic for longer. Isolated galaxies trade drama for longevity, but eventually, they too fade. In the context of the entire universe, isolated galaxies are among the last places where complexity persists. Long after clusters have merged into giant ellipticals and star formation has ceased, isolated galaxies may still harbour faint stars and perhaps even life. They are late bloomers and late survivors. Yet even they cannot escape the ultimate direction of cosmic evolution. Expansion drives everything apart, energy spreads thin, light fades, the universe grows colder and darker. For isolated galaxies, the future is one of increasing separation, increasing silence, and diminishing activity. They will remain what they have always been, quiet witnesses to cosmic history, drifting alone through an ever-expanding universe. Isolated galaxies may seem insignificant at first glance. They are faint, quiet, and difficult to find. They do not dominate telescope images or fill the sky with light. Yet, from a scientific point of view, they are some of the most powerful teachers we have. By studying what happens when a galaxy is left alone, we learn how the universe truly works. To understand the universe, we must understand both extremes. We must study chaos and calm, violence and silence, crowds and emptiness. Isolated galaxies give us the calm side of this story, and without it, our picture of the universe would be incomplete. One of the most important lessons isolated galaxies teach us is about structure formation. The universe did not begin with galaxies neatly arranged. After the Big Bang, matter was spread almost evenly. Over time, gravity pulled matter together, forming stars, galaxies, groups, clusters, and the vast cosmic web. Most of what we know about this process comes from studying dense regions where galaxies interact frequently, but these regions only tell part of the story. Isolated galaxies show us what structure formation looks like when gravity works slowly and quietly. They reveal what happens when matter gathers just enough to form a galaxy, but not enough to create a crowded environment. By studying isolated galaxies, scientists can identify which features of galaxies are fundamental and which are caused by interaction. For example, do spiral arms require interactions to form, or can they emerge naturally from internal motion? Can galaxies become inactive on their own, Or do they need external forces to shut down star formation? Isolated galaxies help answer these questions. They act as control cases. They show us the baseline outcome of galaxy formation when external influences are minimal. This allows astronomers to separate cause from effect in a universe full of complexity. Another major lesson comes from testing cosmology. Cosmology is the study of the universe as a whole. It seeks to explain how the universe began, how it evolved, and how it will end. These theories rely on models that describe how matter, dark matter, and energy behave over time. Isolated galaxies are crucial tests for these models. Cosmological simulations predict how many galaxies should form, where they should be located, and how they should evolve. In dense regions, interactions can hide or alter these predictions. In isolated environments, the predictions are clearer. If simulations predict many isolated dwarf galaxies and we observe fewer, it suggests something is missing from our understanding. If observed isolated galaxies behave differently than predicted, models must be adjusted. This has already happened many times. Studies of isolated galaxies have forced scientists to rethink how dark matter behaves on small scales, how gas cools and forms stars, and how feedback from stars affects galaxy growth. Without isolated galaxies, these refinements would be much harder to achieve. Isolation also helps test ideas about dark energy and cosmic expansion. The size, shape, and distribution of cosmic voids where isolated galaxies live are sensitive to how fast the universe is expanding and how that expansion changes over time. By mapping isolated galaxies and the voids around them, scientists gain insights into the large-scale behavior of the universe. In this way, even the loneliest galaxies contribute to our understanding of the biggest forces in existence. Another powerful lesson isolated galaxies teach us is about the balance between chaos and calm. The universe is often portrayed as violent, exploding stars, colliding galaxies, massive black holes tearing matter apart. These events are real and important, but they are not the whole story. Isolation reveals another mode of cosmic evolution. It shows that the universe does not rely only on violence to create structure. Order can emerge quietly. Complexity can grow slowly. Galaxies can form, evolve, and age without dramatic events. This balance between chaos and calm is fundamental. Without chaos, galaxies might never grow large or diverse. Without calm, nothing stable could last. The universe needs both. Isolated galaxies represent the calm side of this balance. They show us what happens when gravity whispers instead of shouts. This has philosophical as well as scientific importance. It reminds us that not all progress comes from disruption. Some of the universe's most enduring structures are built through patience and stability. From a practical scientific standpoint, isolation is powerful because it simplifies reality. The universe is complicated. Everything interacts with everything else. When scientists study a galaxy in a cluster, they must account for countless influences: tidal forces, gas stripping, mergers, radiation from nearby galaxies, and more. This complexity makes it difficult to draw clear conclusions. Isolated galaxies remove many of these complications. When astronomers observe an isolated galaxy, they can be more confident that what they are seeing is the result of internal processes. This clarity allows for more precise tests of theory. For example, if a galaxy has a certain dark matter profile in isolation, that profile likely reflects the true nature of dark matter rather than environmental distortion. If star formation proceeds at a certain rate, that rate reflects natural processes rather than external triggers. This is why isolated galaxies are often used as benchmarks. They provide reference points against which other galaxies can be compared. They anchor our understanding. Another lesson isolated galaxies teach us is humility. For a long time, astronomy focused on bright, massive galaxies. These were easy to observe and exciting to study. Smaller, fainter galaxies were often overlooked. Emptiness was seen as unimportant. Isolated galaxies changed that perspective. They showed that some of the most important clues about the universe are hidden in its quietest corners. They taught scientists that absence matters just as much as presence. Void regions, once thought of as empty and uninteresting, turned out to be rich in information. They reveal how matter flows through the universe. They test theories of gravity and expansion. They host galaxies that preserve ancient conditions. This shift in perspective is one of the greatest lessons isolated galaxies offer. They remind us that science advances not only by looking at what is loud and obvious, but also by paying attention to what is subtle and quiet. There are also big lessons about scale and perspective. Isolated galaxies force us to confront the vastness of space. The distances involved are beyond every day. Understanding millions of light-years of emptiness separate these galaxies from everything else. Yet despite this isolation, they are still part of the universe's grand structure. They obey the same laws of physics. They respond to the same cosmic forces. This teaches us that the universe is unified. The same rules apply everywhere, from crowded clusters to empty voids. Isolation does not create a different universe. It reveals the same universe under different conditions. Perhaps the most profound lesson isolated galaxies teach us is about time. They show us that change does not always require speed. The universe can evolve slowly and still produce complexity. Some of the most informative systems are those that have had the longest, quietest histories. In a world that often values rapid change and dramatic events, isolated galaxies offer a cosmic counterexample. They suggest that patience can be just as powerful as intensity. Finally, isolated galaxies teach us about ourselves. We live in a galaxy that is not isolated. The Milky Way has neighbours. It has a history of mergers and interactions. Its future includes a dramatic collision with Andromeda. By studying isolated galaxies, we see an alternate path that our galaxy did not take. This comparison helps us understand why the Milky Way looks the way it does. It highlights the role environment played in shaping our cosmic home. It also places humanity in context. We exist during a brief era when the universe is still bright, still connected, still full of visible galaxies. In the far future, isolated galaxies will drift alone, cut off from everything else. By studying isolation today, we glimpse that future and better appreciate the present. In the end, isolated galaxies teach us that the universe is not defined only by its busiest places. Its deepest truths are often found in silence. As we come to the end of this journey, it is worth pausing for a moment. Not to rush forward, not to analyze or measure, but simply to reflect. We have traveled across billions of light years, through vast emptiness into regions of space where galaxies live alone. Places with no crowds, no collisions, no constant motion, just distance, time, and quiet existence. At first, cosmic loneliness can feel unsettling. We are social creatures. On Earth, loneliness often carries pain. It suggests loss, absence, and separation. So when we hear that a galaxy is isolated, drifting alone through space, our instinct is to see something sad or broken. But the universe does not share our emotions. Loneliness in the cosmos is not a failure. It is not a mistake. It is not something to be fixed. It is simply one of the natural states of existence. The universe does not grow in only one way. Much of cosmic history is written in violence. Galaxies collide, stars explode, black holes tear matter apart. These events are powerful, dramatic, and essential. They shape structure, trigger change, and drive growth. Without them, the universe would look very different. But they are not the whole story. There is another path the universe takes, quieter and slower, a path shaped by patience rather than destruction, a path where galaxies grow without shouting, without tearing each other apart. A path of silence. Isolated galaxies are the clearest expression of that path. They show us that the universe does not need chaos everywhere to create beauty. Order can emerge gently. Complexity can arise without conflict. Growth can happen without collision. Some galaxies grow in silence. They form stars slowly. They age gracefully. They change over billions of years without dramatic interruptions. Their light is dim but steady. Their structure is simple but enduring. They are not less important because they're quiet. In fact, their quietness is what makes them special. In a universe filled with noise and motion, isolated galaxies preserve something rare: continuity, memory, calm. They hold on to traces of the early universe, not because they were frozen in time, but because they were allowed to evolve at their own pace. This teaches us something profound. The universe is not designed for spectacle alone. It values balance. For every violent merger, there is a galaxy that never collided. For every starburst, there is a system where stars form one by one, patiently. For every crowded cluster, there is a vast void where almost nothing happens for billions of years. Loneliness, on a cosmic scale, is not emptiness. It is space for stability. It is room to breathe. It is time stretched so wide that change becomes gentle instead of abrupt. When we think about the future of the universe, isolated galaxies give us a quiet preview. As expansion continues, more and more galaxies will become isolated. Distances will grow. Light will fade. The universe will slowly transition from a crowded, connected place into one defined by separation. This future is not sudden. It is not catastrophic. It is gradual. And that matters. It tells us that the universe does not end in a single moment of destruction. It ends, if it ends at all, through long, slow fading, through stars growing old, through galaxies drifting apart, through silence deepening over unimaginable time. There is something strangely peaceful in that idea. Isolated galaxies are not racing toward an ending. They are simply continuing, quietly, until there is nothing left to do but exist. In this way, cosmic loneliness becomes almost meditative, a reminder that not everything must be connected to have meaning. Not everything must be loud to matter. Not everything must change quickly to be important. These galaxies exist without witnesses for most of their lives. No nearby neighbors to reflect their light, no companions to influence their fate, and yet they persist. They are complete on their own. This challenges how we think about importance. On Earth, value is often tied to visibility, interaction, and impact. In the universe, value can also come from endurance, from preservation, from being untouched. Isolated galaxies show us that meaning does not require attention. They remind us that the universe is vast enough to contain many different stories at once. Stories of chaos and stories of calm, stories of collision and stories of solitude. And perhaps this is why they resonate with us. Because in our own lives we recognize both paths. There are moments of intensity and change, and there are moments of quiet growth, where progress happens slowly and privately. The universe reflects both. Cosmic loneliness is not something to fear. It is something to understand. It is the natural result of gravity shaping matter, of expansion stretching space, of time allowing differences to grow. It is not a flaw in the universe's design. It is part of its structure. And in that structure, there is beauty. A galaxy drifting alone through a void is not a symbol of abandonment. It is a symbol of independence, of resilience, of quiet persistence in an ever-changing cosmos. As we end this exploration, it is worth remembering that we are observing these galaxies during a very special moment in cosmic history, a moment when the universe is still young enough for connections to exist, when light from distant galaxies can still reach us, when isolation is rare enough to study and understand. This moment will not last forever. One day, far in the future, observers in isolated galaxies may look out into space and see nothing at all beyond their own stars. The universe will appear small, quiet, and empty. They will not know about clusters. They will not see filaments. They may never imagine a time when galaxies filled the sky, but we live now. We live at a time when the universe still reveals its complexity, when we can see both the crowds and the voids, when we can learn from both noise and silence. Isolated galaxies help us appreciate that privilege. They show us what the universe can be when left alone. And in doing so, they help us understand what the universe truly is. Not just a place of explosions and extremes, but also a place of patience, balance, and quiet beauty. And as we look into the deepest darkness, toward galaxies drifting alone in the cosmic ocean, we are not looking at something empty. We are looking at one of the universe's most honest expressions of itself, silent, enduring, and filled with wonder